like statistics and math like this, once again, can sound like very scary. And indeed, this formula doesn't help much, but once again, I'm going to break this down so you can understand that. So here, what we are doing is we are taking the root mean square energy at frame t. Once again, as we said, all of these audio features are instantaneous, so we take the values for each frame. Okay, so here, the new thing, which shouldn't be like too new for you, is this S of k, which is the amplitude at the sample k, but it's squared this time. So if we have like the square of the amplitude, basically we have the energy. So this guy is the energy of the kth sample. So what we do here is we sum the energy for all the samples in frame t. Once again, like this is just like the sum symbol, and we are like adding up like all the energy for all the samples in frame t. And then once we have like this sum, what we want to do is we want to take the min of the sum of the energy, and we'll achieve that by dividing the sum of the energy by the frame size, which is the number of samples that we have in the given frame. And after we've done that, we just apply the root over here, and that's it. So basically we have the root mean square energy. Now, once again, the root mean square energy is an indicator of loudness, because energy is strictly related to loudness. And the great thing about root mean square energy, and one of the reasons why like it is like overwhelmingly used, at least like in traditional like audio digital signal processing, is that it is less sensitive to outliers than the amplitude envelope. And this is because we're not just like sampling a single sample value for a frame, but rather we're just like getting information from all the samples, and then we take like the root mean square for that's calculated across like all the samples. And so in this way, we are less sensitive to outliers like spikes in amplitude in one sample in all of the frames. Okay, so now what are the applications for root mean square energy? Once again, there are many applications here. I want to talk about a couple of these. So we can use root mean square energy for identifying new segments in an audio signal, and that's because the RMS tends to like change quite a lot when you have like new segments, new like events. And so we can leverage root mean square energy for all things like in audio segmentation. It could be done like for example, like for deciding like whether like someone is talking or it's not talking, and you have like this change and you want to segment who's talking and things like that. And obviously we can also use RMS for music genre classification, and we'll see some of this like over the next few videos in action. The third time domain audio feature that I want to introduce in this video is called zero crossing rate. This is a quite popular acoustic feature used both in speech recognition and in music information retrieval. And it's a quite intuitive one because it provides us information about the number of times that a signal crosses the horizontal axis. So before getting into the math, let's visualize this. Okay, so here we have a signal, simple signal worth of a frame, we can assume, and then the zero crossing rate is equal to the count of like these green dots. Okay, so for each of these green dots, we have a crossing of the horizontal axis. In other words, like for this signal, the zero crossing rate is equal to 1, 2, 3, 4, 5, 6. Okay, now the question is, how do we calculate the zero crossing rate mathematically? Well, here you have the formula for that. Once again, don't be scared about this. We'll just like break it down. Okay, the basic intuition here is that we compare the amplitude value for consecutive pairs of samples, and we look at whether like there are differences like in the signs of those amplitude for those consecutive samples. Okay, so first of all, you should, or we should, familiarize with this sine function if you're not familiar with that already. Basically what the sine function, which is indicated by this SGN, what it does, it gives us back the sine of a given value. So in this case, for example, if the amplitude is greater than 0, the sine function gives us back +1. That's because the amplitude is positive. If the amplitude is negative, we get back -1. If the amplitude is equal to 0, we get back 0. Now, how do we calculate the zero crossing rate like for each pair of samples? Well, what we do is we take the sine for the amplitude at sample k, and then we subtract to that the sine for the amplitude at sample k+1. So we are basically comparing the two consecutive samples here. Now, the cool thing about this is that if we have both amplitude values that have like the same sign, so if they're both plus or minus, what happens here is that we get out of this just like 0. So we don't get like any information regarding, well, we don't get any value that is going to increase the zero crossing rate. But if we have alternate opposite signs, so say for example, like at sample k, we have like a negative amplitude, and at sample k+1, we have a positive sample. So what happens is that we get a value of 2 here. And that's because, yeah, let's just like take a look at this. So if we have like minus here, it means like that we have like -1, -1 minus +1 gives us like -2. We have to take the absolute value of that, so that's equal to 2. But now we are, so this is going to give us information only for one zero crossing, not 2. So we have to divide this 2 by 2, and it's given over here, so that we're going to have just like a value of 1 here. Now what we do is we kind of like sum over all the samples that we have in a frame, and so that we are going to get like the values for all the zero crossings that we have in a frame. Okay, so that's like a simple like mathematical formula that's very elegant for defining zero crossing rate. Now let's take a look at some applications. As I said, this is like zero crossing rate is extensively used in speech recognition, as well as like in music processing. So we can use zero crossing rate for recognizing percussive versus like pitched sounds. And that's because percussive sounds usually tend to have like quite random like zero crossing rate. So like they tend to change like the zero crossing rate like quite a lot, whereas like pitched sounds tend to be like way more stable in the zero crossing rates. And we can also use zero crossing rate as a very rudimentary like monophonic pitch estimation algorithm. In other words, there's a kind of like relationship between like the number of zero crossings like and the pitch. And if we have like a monophonic pitch, basically the idea is like that the higher the number of zero crossings that we have, and the higher the pitch is going to be. Now, this is not bulletproof, and now we have like way more sophisticated monophonic pitch estimators, but zero crossing rate still like is a basic idea that we can use like to get monophonic pitch estimation. And finally, if we want to look at the speech recognition like space, we can use zero crossing rate for distinguishing between signals which contain like voice and signals that are like unvoiced. And that's because when we're like dealing with like voice a voice signal, we usually have like a zero crossing rate like that is like lower than what we have like in unvoiced like pieces of signals. And that probably has to do with the fact that like those unvoiced parts are like noisier, and yeah, and that's the case. In the next few videos, we'll get our hands dirty and implement this time domain audio features and use sometimes also Librosa for extracting them directly from audio signals. But specifically for the next video, we'll implement the amplitude envelope from scratch, and then we'll visualize the amplitude envelope for pieces of music which come from different music genres, so that we can appreciate if there is any difference of amplitude envelope for different genres. Okay, that's all for today. I hope you enjoyed this video. If that's the case, please remember to leave a like. If you have any questions, as usual, feel free to leave a comment in the comment section below, and I'll see you next time. Cheers.